Alright, so now I'm going to teach you arc length, which is basically a fancy word for the length of a curve by the length of the curve. It's the exact length of a curve from one point to another, as measured along the curve. So to find the arc length of a curve, we use integration. So how do we do that? Well, let's take a look back at what we use integration for. So we use integration, we have a function, and we want to find its distance from the area under the curve from point A to point B. So what a integration basically does, definite integration, is it sums up from A to B all the little rectangles, all these infinitely small rectangles, and that infinitely small distance or width of each rectangle is called dx. And so to find the area, if we want to add up the infinitely small areas underneath the curve, right? So if we wanted to find the curve length or the arc length, we would add up all the infinitely small lengths that make up a curve, right? So we're going to add up this distance plus this distance plus this distance plus this distance, and we're going to sum them all up. That's where the integration sign comes from. Sum them all up from A to B. And our infinitely small distance, we want to find that out. So we're going to sum up all of our distances. So we want to take the integral of d, our distance, from A to B of our function. Now, okay, this isn't really helpful. What's our infinitely small distance? Well, we know that the distance formula is the square root of x minus x1 squared plus y minus y1 squared, where x1 and y1 are the distance between the points we're trying to find. Now, in our limit that we're trying to make, we're trying to get these 2 points infinitely close to each other. So their difference in their x's is going to be infinitely small, and the distance between their y's is going to become, again, infinitely small. So in calculus, we call that infinitely small distance delta x. And we call that same infinitely small distance in the y way delta y. So we'll take the definite integral from a to b of the square root of delta x squared plus delta y squared. Now, when anti-differentiating, you have to know what variable you're anti-differentiating with respect to. So you have to have a dx or a dy, a dummy variable, you can call them. Now, because this is a function, we're probably going to want to do this with respect to x. So we're going to make this dx, or delta x. So we need to find a way to pull a delta x out of our integrand, so we can use it as a dummy variable. So the way we'll do that, the first step we'll take is, let's try just factor delta x squared out. So delta x squared divided by delta x squared, well, that's 1. And delta y squared divided by delta x squared, well, that's delta y squared over delta x squared. Okay, and the product rule for radicals is you can break them up. You can break up products within radicals, right? So we'll do that first. We'll do that next. So we'll have the square root of delta x times the square root of 1 plus delta y squared over delta x squared. And well, the square root of delta x squared, that's just delta x. And so we'll have this 1 plus delta y over delta x. We'll just take the square root, the power, the second power out, and have it act upon this all as a single argument. So now delta x and dx is the same thing. So we can now see and easily integrate our arc length of a curve from a to b is just the square root of 1 plus dy dx squared with respect to x, where dy dx is the derivative of our function, of the curve that we're trying to find the arc length of. So let's do an example. So say we wanted to find the area under x squared curve, where y equals x squared, from 1 to 3. Or not the area, but the length of the arc length, the length of the curve from x equals 1 to x equals 3, where our curve is y equals x squared. So if y equals x squared, the derivative of that, dy dx, is just 2x. So we'll just plug that into our arc length function. So we'll go from 1 to 3 of the square root of 1 plus 2x squared with respect to x. So we can kind of simplify this. So we get the square root of the integral from 1 to 3 of the square root of 1 plus 4x squared dx. Now this isn't very easily antidifferentiated, and if I'm not mistaken, you'll have to do some kind of numerical integration, but that's a different video. But it's really that simple. Just figure out the derivative, plug your limits in, and plug your derivative in. And that's how you find the arc length of a function.
I'm Stuart Jeffries. I'm a professor in physics and astronomy at the University of Hawaii, and I'm associate director here at the Institute for Astronomy on Maui. What I do is I'm a researcher, and I research into solar physics and also imaging.
So once you got out of college and you got into your research work,
Yes.
How did you use the higher math like calculus and above in your research?
Okay, well, I use what you're calling higher math, differentiation, things like this, pretty much all the time. When I'm doing imaging work, I have to do a lot of optimization, solve a lot of optimization problems, and during a lot of optimization problems are solved with different techniques, and many of them require derivative information. So I often have functions that are quite horrendous looking that I have to spend 1 or 2 days figuring out how to differentiate. But once I can do it, I have an analytic derivative that I can use, and it makes my codes way faster than if I did something like numerical differentiation. So I actually use it pretty much, all the time.